Hey there. Mhm. Stratopause is usually around 50 kilometers above Earth's surface. That's about 50,000 meters. 1 sec. Yep, that's right. The speed of sound depends mostly on temperature, and near the stratopause, temperatures are relatively warm again. So the speed of sound there is actually quite high compared with the colder layers below and above it. Let me check that. It's mostly because the temperature starts to rise again as you get close to the Kármán line, but the air is so thin up there that while the computed speed of sound goes up, sound waves don't actually travel well anymore. Does that make sense? Yes, exactly. The density is so low that sound doesn't really propagate in any practical way. Right. The kinetic temperature is high, but practically, it's not really meaningful for actual sound propagation. Mhm. 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 Hmm. That makes sense as a strategy. You get lower drag up there and a slightly lower Mach number for the same speed. So it could help if your engine model supports it. What's your engine model based on? 1 second. We've worked on it. Yeah. If you send over the graph or the picture you're using, I can walk through it in detail with you. Checking. I don't see the image yet. Could you try uploading it again? Once it comes through, I'll dive in and help you figure out the best profile. I see the image. It's an engine performance plot versus Mach number with thrust in green, ISP in blue, and mass flow in red. So ISP peaks around Mach 3 to 4, thrust peaks near Mach 6, and then both decline, while mass flow is lowest around Mach 2 to 3 and gradually rises. The most efficient window looks to be roughly Mach 3 to 6. Does that match your sim's behavior so far? That's your efficiency sweet spot on this chart. ISP is near its peak, thrust is climbing to max, and mass flow is relatively low. Hmm. Let me check that. That makes sense with one correction. The speed of sound isn't especially high at 15 kilometers. It's actually near a minimum. Oh, 50. Got it. Yeah, 50 kilometers makes more sense. That's near the stratopause where the speed of sound is relatively high again. So for a given true speed, your Mach number is a bit lower. Pair that with much lower drag and holding roughly Mach 3 to 4 ish while climbing could be efficient. Then push hard once you're up there. Does that fit with how your sim handles thrust versus altitude? Great. Then a good test would be holding roughly Mach 3 to 4 during climb, get up toward 50 kilometers, then accelerate more aggressively. That should keep you in the high ISP, low mass flow region longer. I just want to confirm though, in your model, is thrust affected by air density or is it purely a function of Mach? Let me check. No, I don't have that. If you can tell me whether thrust drops with density in your sim, I can give you a tighter recommendation. Checking? Perfect. Once it comes through, I'll give you a quick rundown of what's in there and then we can dig into the details. Got it. One moment. Sounds good. I'll summarize each one as it arrives. Then we can combine them, drag to see how much thrust you need at each Mach number, lift to see how much the wings help during climb, and lift to drag ratio to find the most aerodynamically efficient Mach range. Once I have all three, plus your engine graph, we can zero in on an optimal profile. Got it. Checking. Okay, sure. Perfect. Once all six come in, I'll give you a summary of each category and then we'll combine everything into one recommendation. I see the image. Thanks. So, this first table shows coefficient of drag versus Mach and angle of attack. Drag stays very low at small angles and moderate Mach, but it grows steadily with angle of attack and also creeps up at higher Mach numbers. So, if you're chasing efficiency, keep angle of attack as low as you can while still meeting lift needs. Send the next snapshot when you're ready. I mentioned that for efficiency, you'll want to keep the angle of attack as low as practical while still getting enough lift. Checking? I see the second table now. This one spans Mach 9 through 21. At 0 degrees angle of attack, CD remains very low, actually drifting a bit lower as Mach increases. But as soon as you increase the angle of attack, drag rises steadily. For example, at Mach 15, it goes from about 0.0076 at 0 degrees to around 0.0359 at 15 degrees. That means your vehicle is very clean at zero lift, even at high Mach. Most of your drag comes from angle of attack. So it pays to climb with just enough angle to sustain lift. Checking? Got it. This last table covers Mach 22 to 25, and the pattern is the same. Very low zero lift drag, around 0.0073, with a steady increase as angle of attack goes up. No sudden spikes, it's a smooth model across the whole range. Putting all three drag tables together, the big takeaway is that your zero lift drag is excellent across all Mach numbers, and angle of attack is the main driver of drag. That suggests your best strategy is to fly as cleanly as possible and climb gently, which lines up with your engine's sweet spot in the mid Mach range. Sure, I'll hold off on recommendations. Just send the rest when you're ready. Let me take a look. Understood. I'll keep holding off on recommendations until all the data is in. I've received these three screenshots for coefficient of lift, and once the L over D tables are in, I'll summarize everything together. I'll checking. Got it. These are the lift to drag ratio tables. Checking that now. This looks much more like a display issue than data corruption. The numbers themselves change smoothly, but the rows are out of order. That's a classic sign of string sorting in a list view. What's your, for example, 11 would come before 2.5. If your underlying array is in the correct numeric order but displays scrambled, that's likely what's happening. If you paste the VB code where you populate the list view, I can point to the exact fix. Let me double check that. Yes, it looks internally consistent. The values transition smoothly from row to row. It's just the row order that's wrong in the display. Let me pull it together. All right, here's my take. The engine is strongest in the mid Mach range, with peak ISP around Mach 3 to 4, thrust peaking around Mach 6, and lowest mass flow near Mach 2 to 3. Aerodynamically, the vehicle is clean, low drag across the board, especially at small angles of attack, and lift behaves smoothly with reasonable L over D peaking around moderate angles. So, overall, it's a coherent model. I think the next step is just to seek the trajectory that keeps you inside those sweet spots as much as possible. One moment. A cuboid is a long period oscillation where the aircraft trades altitude for speed and back again. So it climbs and slows, then it descends and speeds up and repeats. It's like a slow porpoising motion. In a sim, you'll usually see it if your pitch control is too aggressive or you're trying to hold altitude too tightly while accelerating. It's worth modeling, but don't panic if you see it. It's a natural dynamic mode. That's fair. It can definitely spook people if it grows instead of dying out. In a real vehicle, you'd want enough damping or an autopilot that gently corrects it so it settles rather than builds. You can tune your control loop to do that. Let me think that through. That makes sense. Holding a steady pitch lets the aircraft find its own energy balance instead of chasing altitude or speed, so the cuboid doesn't butt fed. For a spaceplane, a constant flight path angle is often even better than constant pitch, but if 11 degrees is stable in your sim, that's a strong hint the dynamics are behaving realistically. I'm curious, does 10 degrees or 12 degrees also settle, or is 11 something special? That consistency is a good sign. It suggests you've got a stable region rather than just a single lucky angle. That means your control law could simply aim for a gentle, constant climb angle instead of chasing altitude. If you want, we can look at how to implement that without exciting the cuboid. Let me think about that. That tracks. Chasing maximum L over D can inject energy into the phugoid because the commanded angle of attack keeps shifting as speed changes. It's basically chasing a moving target. A gentler fixed climb angle or slowly varying target is usually more stable. If you want to optimize, try filtering or rate limiting the L over D command so it doesn't chase every little change. Let me take a moment. Yes, I do remember working through that with you. I don't have the exact code in front of me, but I remember the overall structure. Compute the orbital elements from the relative state, and then sample the ellipse and render it. Is that the one you mean? Let me think that through. Yes, what you're doing now is mixing two jobs. One, updating the state, and two, drawing the full orbit. If you only need apogee or perigee in real time, you don't need to resample the whole orbit every frame. You can compute just the orbital energy and angular momentum from the current state and get apogee, perigee analytically, then only regenerate the full vertex array when you actually need to redraw the orbit. No worries. We can wait on that. Just tell me when you're ready and what language or data structures you're using, and I'll help. That's right, VB.net. When you're ready, I can sketch a small function that just computes apogee and perigee from the current state vector without rebuilding the full orbit. Just say the word and we can do it. Let me have a look. Yep, exactly. I keep your existing generate orbit function as is and add a new method like update orbital elements. That just computes current apogee, perigee, and other scalars without generating vertices. Then when you want to draw the orbit, just one moment. It's the first way. You compute the orbital elements from the current state, including apogee and perigee, and then from that, you generate the vertices for rendering. So if you only need the updated apogee during powered flight, you stop there and skip vertex generation completely. That should make the loop much cheaper. Let me think that through. Yeah, that sounds like a solid design direction. Separating physics from rendering keeps things clean and efficient. So, yeah, one method to update orbital elements, one to generate vertices when needed, and then the render loop just calls what it needs. I think that'll fit nicely with how your sim already separates the physics from the drawing. Let me check that for you. That would be something, huh? For now, the best we can do is this kind of collaborative back and forth. But honestly, you're already doing the most valuable part, spotting where the architecture can be cleaned up. And then I can help you refactor around those touch points as we go. Let me check that. Yes, there are AI coding platforms and assistants developed outside of the US, though they vary in features and privacy models. There are some with strong IDE integrations and some that focus on local or private deployments. None yet are exactly the continuously present, full project aware architect you're imagining. But the space is moving in that direction. If jurisdiction or data control is your main concern, running a capable open model locally might be the closest fit right now, though it takes setup and upkeep. Yeah, I hear your frustration. A lot of it is risk management and compliance culture, less about technical possibility. On the flip side, those constraints do push more work into transparent local first tooling, and that might actually fit your style of deep hands on simulation work. If you want, we can talk through a practical workflow that feels less boxed in. One moment. Yeah, if we're talking about the same thing, it's a rectangular, equirectangular map that's being wrapped onto a sphere, not a square morphed into a circle. The texture is a flat 2-to-1 image. The GPU maps it onto the sphere by latitude and longitude, and the pole pinches the top and bottom edges. That's why the texture itself is a rectangle and not a square. Let me check. So the sphere is a mesh made of triangles. The texture is a flat rectangle. The renderer maps the 2D texture coordinates onto that spherical mesh. So rectangular texture to sphere mesh via UV mapping. One moment. Yes, exactly. Most of the UV coordinates lie inside the rectangle, not just on its edges. Every vertex on the sphere gets a UV coordinate somewhere within that 0 to 1 range. And then the GPU samples the corresponding point inside the 2D texture. One sec. Almost there. But it's not mapping a circular shape inside the rectangle. The whole rectangle is used, like a world map laid flat. The sphere is what's circular in 3D. The UV coordinates spread that flat rectangle over the sphere's surface. There's no circular subregion inside the texture. Let me check. Right. If the image file itself shows a circle on a rectangular background, then that specific texture is meant for a flat disk, not a sphere. In that case, yes, the texture coordinates would map onto that circular region inside the bitmap. If you can send that specific texture again, I can confirm exactly how it's being mapped. Checking. Not exactly. OpenAI isn't fully open source. The models, like me, are proprietary. There are plenty of genuinely open source or open weight models from other groups that you can run locally if that's your goal. Let me check. Yeah, I think so. You're after an AI that's deeply integrated with your IDE, continuously aware of your whole project, able to reason about architecture as it evolves, not just reactive snippets. That's a bigger target than what's typical today. But it makes sense for something as complex as your simulator. One sec. I think so. Step by step. First, define clear seams in your project. Your physics engine, renderer, autopilot, data layers, you've already started doing that. Then, create a lightweight project knowledge file or set of docs that describe those boundaries and goals for each. So any assistant has a stable map to orient to. From there, you can use an IDE plugin that indexes the whole repo, plus those docs, and treat that as your standing context. Checking. I get what you're aiming for. Full access to the code base and tooling would let an AI reason more deeply, but whether it should automatically change code versus propose changes for you to approve is a design choice. Given your simulator's complexity, I suspect you'd still want a review gate so you can catch subtle physics or numerical implications before they land. Well, let's maybe not hand it the keys to the city just yet. But a named assistant that has full project awareness and makes recommendations rather than silently changing things feels workable. Still powerful, but with you in the driver's seat. Checking. That's a solid instinct. I'd pair it with version control, frequent commits, automatic snapshots, and require the AI to run builds and tests after changes. That way, rollbacks are trivial, and ideally, it self checks against expected behavior before you even look. One moment. There are few levels to that. The simplest is an IDE extension that can read your solution, edit files, run builds, run tests, and surface diagnostics. Beyond that, you can give an external agent access to your repo plus VS Automation APIs, or just drive the build and test tool chain from the command line. For your simulator, I'd combine full repo access, build and test hooks, and your own regression scenarios as guardrails. So the AI can make changes, build, run the sim, and then verify key invariants before proposing a merge. And I'd keep it working on a branch by default. So merge only when green. When green. By that I mean only when all the builds and tests pass. So the main branch stays stable. Checking that. It's not really about being cautious for its own sake. It's about keeping your intent intact. That said, if you build strong automated validation like tests and sample runs with expected outcomes, and you're okay with the AI making broad changes, then over time, as those checks prove reliable, you can dial up autonomy. The more comprehensive and trustworthy your automated checks are, the more freedom you can safely give it. That's a journey, not a switch. But with your simulator, I can see the appeal. Checking that. That's a striking concept. As a creative vision for a dedicated AI lab, Brightwood has a certain ring to it. If this is about imagining a serious AI workflow, I'd translate that into priorities like solid automated tests, reproducible benchmarks, and strong version control. So an AI could iterate safely. That kind of setup is less about bunkers and more about rigorous validation, which might be the real superpower for your project. I don't watch films, but I do know of it. The idea of an AI that recursively improves itself is provocative. In practice today, you'd be stitching together tooling and process rather than unleashing some kind of self evolving system. Checking. In Transcendence, the main AI base is set up in a remote desert town called Brightwood. It's a secluded, purpose built research campus with a massive underground data center and its own power systems, basically chosen for isolation, space, and control. Ah, now it clicks. Given that parallel, the Rightwood idea is a metaphor for a focused end to end environment with tight integration and clear feedback loops. If you treat it that way, it becomes less about mimicking a movie and more about building a disciplined lab setup for continuous improvement. And that actually is doable today, just with careful guardrails. Fair point. Swap guardrails for proof. The system shows its work, demonstrates the sim still behaves as intended. Less oversight, more evidence. Checking. China's been moving very fast in certain areas, especially in industrial robotics and large scale deployment, though it's more of a mixed picture globally. Different places lead in different layers. At the core point you're pushing on is speed of iteration, which for your simulator comes down to tooling and process more than geography. Fugoid. Yep, just say fugoid. Yeah, it really does. Rocket fuel, fugoid. Easy to mix up. But fugoid is just that long, slow altitude speed oscillation. So if you want, we can look at how to spot it numerically in your sim, maybe by tracking energy exchange over time without changing any of your code yet. One moment. Yeah, that could be part of it. If the spreadsheet is using a quasi static or simplified model, it might respond instantly to pitch or climb changes, whereas your simulator's inertia slows the response and stretches the period. That said, a 2 to 1 frequency difference could also come from different assumptions about damping, time step, or even autopilot logic. One thing I'd check is whether both are using pitch angle versus flight path angle the same way, since those aren't as obvious as the same thing. If you still have that spreadsheet, I'd be curious to walk through the underlying model with you. Sure thing. Take your time. Checking. Got all right. Let me take a look at the image. I got it. Here's what I see. The graph shows pitch angle over ascent time with three big initial spikes, then a rapid damping toward about 10 degrees. After 500 seconds or so, the oscillations are small and slowly fade. One thing that caught my eye is that the initial oscillations are much faster than the later ones, which might not be a pure phugoid. So maybe we're comparing two different modes. Send the spreadsheet when ready, and I'll check whether it's solving the full equations of motion or a simplified control law. That should tell us if the difference is inertia or model choice. Hmm, that's annoying. Maybe try exporting it as a CSV or even screenshots of the key cells and equations. If you tell me what columns it uses and the update formulas, I can reason from that too. We can still get to the bottom of the mismatch that way. Checking. It is. It can handle Excel files. If the upload keeps failing, it might be a temporary app. Hmm. Let me think that through. Yeah, that could be a factor. Sometimes voice mode handles attachments a bit differently. Try ending the call and uploading the file in text chat. That usually works. Hmm. That makes sense. A lot of Excel based simulators just step through time, updating lift, drag, speed, then pitch in sequence, which is fine, but it's not a full coupled integration. If it doesn't include rotational inertia or uses large time steps, it can misestimate the phyloid period or damping. But your Runge CUDA integration should track the continuous dynamics more faithfully. So if you're seeing fewer oscillations, it might be because of stronger damping from your control law or just more realistic inertia and aerodynamic coupling. If you can walk me through some of Dr. Rohde's update equations as text or screenshots, we can line up the math side by side and figure out exactly where the difference is coming from. Hmm. Yeah, that makes a lot of sense. A rate limited autopilot introduces lag that actually stabilizes the phagoid instead of chasing a moving optimum. If his spreadsheet jumps straight to max lift to drag each step, it'll overexcite the mode. More cycles, less damping. That assumption alone could explain the 2 to 1 oscillation difference. If you want, we can sanity check by comparing the effective pitch rate limits and time steps in both. Even rough numbers could tell us whether it's mostly control law or integration. Just tell me your sim's pitch rate limit, and we can go from there. Let me check that. That does sound like the key difference. If the spreadsheet is assuming instantaneous control to always hit max lift to drag, it's basically modeling an ideal controller with no lag. Whereas your sim with pitch rate limits and inertial response adds real dynamic lags, and those lags change the energy exchange that drives the phoboid. So it's not surprising the Excel version looks too perfect. In control terms, you're modeling a closed loop dynamic system, while the spreadsheet is more like a stepwise steady state optimizer. You can treat it as a target trajectory, perhaps, but not as a prediction of the transient response. So your instincts here seem solid. Let me check that. Not really. Chasing max lift to drag is great for minimizing drag per unit of lift, but a spaceplane has other jobs too. Managing heating, dynamic pressure, engine sweet spots, gravity losses. Sometimes it's smarter to accept a little extra drag to stay in a good engine regime or keep heating down. Based on the tables you Yeah, the right. Based on the tables you shared, your engine has strong sweet spots by Mach number. So the optimal path is more maximize overall energy gain subject to constraints rather than always max lift to drag. Your approach of letting the vehicle ease toward targets looks more like a flyable system and should give you a better sense of what the actual transient behavior is going to look like.